And all right, let me hit just a couple of issues before we start recording, and reminding everyone, this is also for people who are listening, because not everybody's here, only 4 are here. Let me make sure I do have 4 marked in the roll book. 1, 2, 3, 4, yeah. Okay. We have basically 2 weeks left of class, and then counting today, and then I think technically finals are Tuesday of the 2 weeks from today. I think it's the 31st is supposed to be the first day of finals. Is that right? And that's, yeah, is that on a Tuesday? Okay, I thought that was the case. So that means, folks, we only got 4 more classes today and 3 more, and then I'll be here for finals week if you need to bring stuff by. But I still have, it's kind of unbelievable at this point in the term, 2 people have not turned in test 1, 2 people that have not turned in test 2. I may have got one of those just today. At least 3 people, 4, 5 people, something like that, that haven't turned in test 3. And I've only got 3 test 4s in, except I may have gotten some in today. So I only got 2 more weekends and 3 more classes to get these done, and we'll have a test on this chapter, and then the one on the next 2 chapters combined will be your last test. So you still got some more tests coming. So please get these caught up.
Are you giving us the final, the 31st, or you gonna give us?
No, I'll give it to you the last day of class, and then you'll have that weekend to work on it.
You said 31st is the last day of class? Or
No, 31st is, I think, technically the first day of finals.
That's what I'm asking. So you gonna pass it out the 31st, or you gonna give it?
No, I'm going to give it to you the last day of class, which is appears as Thursday. Yeah, and then you have the weekend to work on it.
And then turn it in on the 31st.
You can turn it in on the 31st or the 2nd, because that's also during finals time.
But you don't have to come on that Thursday, the 2nd.
No, yeah. If you want to turn it in on Bessemer campus, you can do that. You don't have to come here, but I will come over here as normal and be here Tuesday and Thursday evening full time for anyone who wants to come in. If you have questions, you can ask me questions then too. I'll be here on both the Tuesday and Thursday evening. Hopefully I'll be working on grading papers and getting things done, doing emails, all sorts of stuff like that. I've got plenty to do, so I'll be here approximately the same times as I've been coming, 4 to 6 basically. I usually say at least till 6. Okay, Kayla, right? Okay. So now we're up to 5. All right. Now, if you want to have another class that Tuesday, the 31st, then we could have the test due on. Okay, I didn't think you did. Okay, I thought maybe that's what you were aiming for. Okay. All right, so that's where we're going to be going as the term goes. Now, I haven't seen anything, and I sort of doubt if there is anything on student course evaluations. I don't recall having those in the summer, but I don't know for sure. You haven't heard anything, sent any emails or anything. Okay. I doubt if they're doing that. I would have thought they would have, but I don't think they do it in the summertime. All right. One more issue not having to do with classes or grades or tests or anything else. Today is a voting day. This is the day when we vote in the primary runoffs. So whether you voted Republican or Democrat, there are runoff elections on both parties, and even if you didn't vote in the primaries, you can still go and vote in the runoffs. Please do, okay? Please do not let a voting day go by that you don't vote. So please, as soon as I leave here, sometime after 6, heading straight to the polls, okay? I would have done it on the way in this morning, but I was running not late, but I just didn't know if I had time. Usually there's not a crowd on days like that, but I thought there'll be a crowd today and then I'll be late for work. So I've got time, so I'm going to be leaving here sometime after 6 to vote. So please vote, folks. Please vote. As I told my other classes, my saying is, if you don't vote, you have no right to gripe. And I like to gripe, so I want to have that right and do it. Okay. All right. Any questions on anything we've covered so far? All right. What we have here, my note to myself here is that we're in Chapter 17, Basic Electricity, 17.8, Parallel Circuits, and we're on page 475, top of the page, example 2. Okay? Here's the data. What they have is a circuit that looks a lot like the one on the right here. Okay? It says find the total current in the circuit shown in this figure. Now, it's not exactly this figure, but pretty close to it. Where R1 is 23 ohms. Let me get my pen activated. Okay. R1 is 23.0 ohms. R2 is 14.0 ohms. R3 is 5.00 ohms. Your E over here, 90.0 volts. That is an enormous voltage. This is not a very realistic problem, okay? Not very realistic at all. Okay? Now, the question is to find the total current. So what we're looking for is I, which we're going to call I, but you could call it IT if you wanted to. Now, what would be your approach to this problem? There's really several you can do. They have a suggestion in the book, but you don't have to follow that if you see a way you understand better. What would be your approach to this problem? Anybody? Second? Adding the resistors? Okay. That is what you would do in a series circuit. What kind is this? What kind is this? Not series, but parallel circuit. Now, you do add something in a parallel circuit. It's not the resistances, though. It's what? It has to do with the resistance. What do you add in a parallel circuit? There's actually two really good answers to that question. I'll let you choose which one you want. Anybody? Anyone at all? Okay. Actually, to get the equivalent resistance, you add the reciprocals of the resistance. That's what I was getting at. Okay? So basically what you're adding is 1 over R1 plus 1 over R2 plus 1 over R3. Now, the easiest way to punch those in on a calculator is to look for the 1 over X key or X to the minus 1 key. Okay? Do you have that on your calculator? It's either 1 over X key or X to the minus 1 key. If you look at the top of the page, you got it. Okay. So, if you're going to use that key, then I would press a 23, press that key, plus 14, and press that key.
So you add a plus sign after? No. just do the.
Okay, yeah, you're adding the reciprocals. So if you press 24 and press the 1 over x key or x to the minus 1 key, you're adding the reciprocal of that to the reciprocal of the second one. So after the plus sign, 14 reciprocal plus 5 reciprocal equal. Okay, you get a pretty small number, right? Okay, so let me go through those commands again. 23, is your key x to the minus 1 or 1 over x? Okay, x to the minus 1 plus 14, x to the minus 1 plus 5, x to the minus 1 equal 0.3149. Okay? Now, does anyone recall what those three added together gives you? Hint, it's not the equivalent resistance. What would those three give you? What did you hit every resistance? We're Southerners. We hit things. We don't press things. Okay. Let me take a look.
Coming up.
Okay. That's 34, I think, is the first one. Is it? 20.
Come up is.
Okay, that's okay. That's all right. That's okay. Yeah, that's perfectly all right. That's just in fractional form. Now the next thing you hit is this key again, the reciprocal key again, and press equal. Okay, and that's exactly what it does. Okay, now I don't know how you make your calculator do the calculation. You would think it would do it, but what you can do is write down 1610 divided by 507, and then punch those numbers in. In fact, well, yeah.
I do it on this. So that you're just saying that's going to be the answer.
That will be your answer. What you do with this number right here, is 1 over the effective resistance. Now, they usually call it R. Some books will call it REFF for effective, or total for total. I don't like that for parallel. Or equivalent resistance, REQ, any of those. And that's what hitting that reciprocal key one more time will do. And then what answer does that do? So you hit reciprocal, I'm sorry, x to the minus 1 again. So let me, sorry. Okay. Yeah, my eraser is not erasing. Okay. All right, try this again. Then you hit the x to the minus 1 key again, and when you do the division, what do you get? 3.1755. Okay, we had 3 significant digits everywhere, so this will be 3.18 ohms. But you might want to leave that 1755. Hang on to that for just a minute, because we're not through. That's not your final answer. That's just your effective resistance. What we're looking for is the current. So how do we find the current? Okay, I is equal to E over R. Now, if you have the 3.1755 still on your screen or something like that, you can do that reciprocal key again to move it downstairs again, and then multiply it by E, which is 90. So you can do that number there that you have, do x to the minus 1, and then do times 90. And then press equal and see what you get. 28.3 what? Okay, leave, yeah, but 28.3 what? What unit? Current. Amps. Very good. Okay. So I don't usually round here. I go on and finish the problem and just round the last answer. Like you got 28.34, round that to 28.3. Okay. Let's see how the book did. Look at that. Yeah, and we did too. It's just that I did it a little bit easier, so I'm lazy. Okay. Okay, well, what we're doing here, when you did the x to the minus 1, you took this thing and put it there. That was your thing. And then you multiply that by E, and that gives you E over R. Okay? It's doing the same thing. If you wanted to, you could clear the screen, put 90 divided by 13.1755. That works, 3.1755. I can't talk. And that gives you the same answer. Okay? Now, I said there were two ways to do this problem. Okay? Okay? So we're going to leave it on the screen for right now. Here was the second way you could have done this. Okay? This worked just as well. You could have said the total current coming in splits into an I1, an I2, and an I3. Okay? And you could have calculated each one of those, just the same formula we did before. I1 would be E over R, E divided by 23, plus I2 would be that same E, because it's 90 volts across there, 90 divided by 14 plus I3 would be 90 divided by 5. Add those three currents together, that's your total current. So if you see that better or easier or more clearly than you do effective resistance, all those reciprocal keys, that works just as well. You can try that if you'd like. If you don't have to. But see, there's sometimes more than one way to skin a cat if you don't like cats. But never mind, I'm just kidding. Okay. Do each of the currents. You don't have to do it. It's just another option. Calculate the current going this way, the current that way, and the current that way. Current going this way is this voltage, because that voltage is across all three of those. Okay? So 90 divided by 23 plus 90 divided by 14 plus 90 divided by 5. If anyone has a calculator, see what that gives you. Exactly the same answer. Okay? So, like I said, more than one way. So when you said add, I said, what are you adding? You're either adding the reciprocals together and then taking the reciprocal of that and then multiplying that, or you're calculating the currents and adding those together. Both of them work. Okay?
So the I will be the current.
I is the current, and you're looking for the total current, so you add I1 plus I2 plus I3. I had you do it all at once, but you could have done them separately, had you chosen. All right. Now, while we've still got that on the screen, it says find the current through R2 in this same figure. So now we're looking for current I2, the current in R2, going through R2, which is I2. And that's pretty easy to do. What would that be? I2 is equal to?
But you divide the
E divided by R2. Exactly. E divided by R2. And that would be 90.0 volts divided by 14.0 ohms. Actually, those extra zeros are not necessary, but you can do it. 90 divided by 14 is a little bit more than 6, right? Bless you. Second?
At 6.428.
So 6.42. So let's just round it to 42. And that would be, oh, yeah, you're right, 43. And that would be in what units? Amps, of course. Okay? Okay, 43 amps. Now, if you had done, like I said, first the current through R1, then R2, then R3, done them separately, and then add them together, you'd already had that current through R2, and you could have just written it down. That's, the current through R2, which is I2, and that was for 6.43 amps. Very good. All right. Now, I'm going to erase all this unless some of you need it up a little bit longer. Anybody? Okay. Now, example 4 says find the equivalent resistance of the value of R3 in the circuit shown in this figure. No, the equivalent resistance and the value of R3 shown in this circuit. Okay? Now, that one looks more like, even though they're the same circuits, but it's just drawn more like my first figure here, the A figure, so I'm going to use that one now. They tell you here E is equal to 115 volts. E is equal to 115 volts. That's more like what alternating current would be. Okay? The I, they don't put an arrow on that one, but most of the time we put the arrow like that. And I is 7.00 amps. I equal 7.00 amps. I can't write. Oh, I did an ohm. No wonder I can't write. Okay, amps. Okay. R1 was 38 ohms. R2 is 49 ohms. Okay. And R3 we don't know. All right. Now it says find the equivalent resistance and the value for R3 in the circuit. Now, it doesn't matter which one you do first. You can do either one of them first without any problem at all. Which you want to try to do first? Equivalent resistance or R3? What would be your first step? Okay. Now how would you find the equivalent resistance if you know the voltage and the current? R is equal to E over I. Absolutely perfect. Okay? And that will be your equivalent resistance. So that will be 115 volts divided by 7.00 amps. And you tell me what it is.
16.
A little louder.
16.
16.428. So, I'm going to write it all down for now. 428. Okay? And what would that be in? Units? Ohms. Okay. Now, to answer your question, what is the effective resistance? I would then say R is equal to 16.4 ohms. Okay? Now, yeah, in fact, you don't need the 2.8 ever. Okay. Now, the second part of the question said, what is the resistance R3? How are you going to get that? Second?
You said how to find R3?
Right.
Subtraction?
Okay. Here's the problem with that. In a parallel circuit, resistances don't add. The reciprocals add to the reciprocal of the effective. So you could go that route if you wanted to. There's a much easier way. Okay? You know the voltage, and, oh wait, you're right, there's not an easier way. Sorry about that. Yeah, I thought there was. Okay, there are two ways you can go, very similar to what we did before. One is what you were sort of suggesting, I think, and here's what that was, I think. Tell me if this is what you meant. 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3. We know that, right? So since we're looking for this one, you can subtract those reciprocals from each other. So 1 over R minus 1 over R1 minus 1 over R2 is equal to 1 over R3. Okay? And since you have your handy-dandy calculators that do that reciprocal for you very easily, you can do it just like that. Okay? In other words, if you still have that 116.428 on your calculator, I would leave it right there and then hit your reciprocal key, x to the minus 1, then do a subtraction of 38 and hit that reciprocal key, minus 49, hit that reciprocal key, press an equal, and that gives you a number, and hit the reciprocal key after that, and that gives you R3. Because, see, that gives you 1 over R3. The next reciprocal key will give you R3. Did you follow what I was meaning? What's that?
This computer mode is set different. That's what that stuff can come out the way it is. Now I can't put it.
Okay, I don't understand what you're saying.
No, I said, I guess the mode is set up on
Oh, the
here.
mode. Okay,
And I
I
don't know
got it.
how to change it. I'm trying to get this off.
Okay. Ooh, wow. Okay. I see an on button, but I don't see an off button. How do you turn this thing off? Let me try shift on. That doesn't work.
I need delete and see it. That's a brand new calculator.
Okay. Where is it? OFF.
Isn't that one?
There's one right there, over that key.
Right here.
So to shift that.
Oh, okay.
Okay.
So now we turn it on.
Okay.
But look.
Oh my word. Okay.
Throw the whole calculator.
Is there a clear key? Okay.
That's a delete and then I can see you using being clear, right?
Well, I thought so. All right.
Brand new.
Let's see if there's. Oh, here's a clear here too. So let's do a shift clear. You want to
Just
clear
clear.
the setup,
Just
memory,
clear
or all?
Just it's brand new, so just clear out everything.
All?
Yes.
Okay.
Because I was trying to check.
Reset all?
Yes.
You want yes?
Yes.
Okay. Equal is yes. Okay. Reset all. Press AC key. Ah.
Now
There you
it's
go.
gonna work like it's supposed to.
Okay. Don't know. All right. So what you want to do, if you had that 16.428, you can enter that if you want to. That's your R. And then do your reciprocal key for that. Then a minus. And then your 38, which is R1, reciprocal key. Minus your 49 and your reciprocal key. Then press equal. And that gives you 1 over R3. Does it mess up?
Mine's coming like it did a fraction.
Okay. All right.
We should be able to change the mode on this.
Yeah. All right. Has anyone got an answer yet? What's your R3?
With the 70, I got R3. 70.
70? Okay, R3. Okay, you hit that key.
70.1672.
Okay. Whatever you got there, then you hit another X to the minus 1, and that gave you your 70 point what? 16. Okay. So we'll round that to 70.2 ohms. Now, here's the question, folks. Is that a reasonable answer? Is it reasonable for this to be 32, that to be 49, this to be 70.2, and you have an effective resistance of 16.4? Yes, very reasonable. Because in a parallel circuit, the effective resistance is less than the least of these. The least of those is 32. It certainly is reasonable. Okay? Let's see how the book did. Did they?
Yes.
Good for them. 70.2 even, on the nose. Somebody's nose. All right. And they have those steps up at the top, I think just like we did. And there we have it. Okay. Now, I think I'm ready for the next slide. Are y'all? That was example 4, right? Okay. We did this pump problem. We talked about that last time. Here are our characteristics of the parallel circuits. Okay? When you have a parallel circuit, okay, that means 3 or more, 2 or more different branches that it's going to, then the total current is the sum of all your little currents that go to each branch. Right? Your resistance is the reciprocal of your resistance is the sum of the reciprocals of all the individual resistances. That's that good old resistance formula for parallel circuits. So a series circuit, you just add them up. R1 plus R2 plus R3. For a parallel circuit, that's the sum of the reciprocals equals the reciprocal of the total. On a series circuit, the same current is going through every resistor. So those are all the same. On the series circuit, your voltage is the voltage across the first resistor plus the second plus the third. The voltages add up to the total voltage of your battery, but in a parallel circuit, all the voltages are the same because it's the same potential difference across each resistor. Okay? So those are the rules, the characteristics of parallel circuits. All right. Now, the place where this is important, as in your home, or possibly place of business, if you put too much in parallel across the same voltage, your current goes up and up and up. You put a resistor here, and another resistor there, and another resistor there, and you keep adding resistors in parallel, then that demands more current. I1 plus I2 plus I3 plus as many as you want to. Your current soon gets so high that you could start a fire. Okay? In other words, hopefully your circuit breaker will break or your fuse will blow. Okay? Now my wife and I got married and we moved to Birmingham. A friend of ours had helped my wife find a house to rent, and it was a neat old house to look at. It was a drafty old house to live in, okay? and it was an old house, and Karen liked old things. Thank goodness. That's why she married me. Okay. So, I don't even know how old the house was, but it seemed pretty old. And we moved in, and they said the kitchen has been updated. None of the other rooms have been updated. Three big old bedrooms upstairs. Each one of them had one plug on one wall. 4 walls around there, only one plug on one wall. So we had to put extension cords and stuff and run to have all our clocks and our lamps and everything else. And one of the rooms didn't even have an overhead light, so we had to have lights in there. Big old rooms, okay, so we had to do a lot, okay? But that was okay. One room had an air conditioner in it, not the master, but we could turn it on and it would cool most of the upstairs okay. We were only in there one summer, so we lived through it. But that kitchen that had been updated, it had plugs all around the wall. Okay, a plug for the refrigerator, a plug for the microwave, a plug for the coffee maker, a plug for, just all around there. Plugs. We thought, all right, this is fine. And they all looked fairly new. It did look like an updated kitchen. But what we found out is that if you were, say, fixing coffee in the morning, and happened to put the toaster on, and then the refrigerator kicked in the compressor, everything went out. Because all they had done was take that one circuit that used to go to the kitchen and just put more parallel circuit after parallel circuit after parallel circuit in, and it looked like it was all brand new, but you could not run generally more than 2 things at once. Now, if it's a real low energy requirer, like maybe a light bulb or a fan or something like that, maybe you could get by with 3. But if you use 2 or more things that required a lot of current, like your refrigerator compressor required a lot of current, anything that produced heat, toaster oven, coffee maker, anything like that, you could not run more than 1 or 2, because you would see the lights go down and you'd say, oh no, we're going to blow another fuse. And it had fuses, not circuit breakers. So I think we personally kept, and this is how long ago it was, you remember Big B, anybody? That was the old drugstore. Huh? Yeah. Okay. It was the Bruno family. That's what the B stood for. They had all the grocery stores in town. They had the major drugstores in town. So we kept the local Big B in business by buying fuses. Okay, so we were always buying fuses. We had a stash of fuses there because anytime, and you couldn't predict when the refrigerator was going to cut on, so you might be doing all right, but if it cut on when you were doing something else, there we go, another fuse. So head back to Big B and buy some more fuses. All right, enough of that. So that's the nice thing about parallel circuits. You can just keep adding things to it, but the not so nice things, they draw a lot of current, and you could either start a fire or you're going to blow fuses or circuit breakers. And when you do it, don't just put in a bigger fuse or a bigger circuit breaker. Change your circuits, because you got too much going through those. All right. Now, that finishes 17.8. There's only 2 problems there. No, I'm sorry. There's 4 problems, but only 2 odd problems. So you can do number 1 and or number 3. They have pictures for both of those. Now in 17.9, we're moving on to what we call compound circuits. Okay? These are circuits that have some elements in parallel and some in series, and you can have an amazing array of possibilities. Okay? Now what you do in a circumstance like this, a compound circuit contains a combination of resistances in series and parallel arrangements. To simplify solving this kind of circuit, we apply the rules for series and parallel circuits to find the equivalent circuit that reduces to a circuit with 1 resistance. Okay? Here is a compound circuit. Okay? we have resistors 1 and 2 in series, and they are parallel with resistance 3. So it is a combination series and resistance circuit. So what do? Go to the most basic combination you've got, R1 and R2. How do you handle that resistances in a series circuit? You add them up. So R1 plus R2, we're now going to call R4. Okay? Just add R1 to R2, that's your new R4. Redraw it if necessary. Okay? Now you got two resistors in parallel. And how do you do that? What's the equivalent resistance there? Well, you're going to get R5, but how do you get that?
Adding R3 and R4.
Add what?
R3 and R4.
Not quite. These are in parallel. How do you add parallels? 1 over R4 plus 1 over R3. The R5 would be 1 over that. Remember, in parallel resistors, you add the reciprocals, and it yields a reciprocal. Okay? So, here's what you do, and you set it right. R1 plus R2 is equal to R4. But these are in parallel. So on these, we say 1 over R4 plus 1 over R3 is equal to 1 over R5. Exactly. Okay? And then whatever you get, plugging in numbers there, be sure you reciprocate the last, and that gives you R5. Okay? All right. That, yeah.
So on R1 and R2, those are series?
These are in series. See, the same current goes through both of them. So you just add the resistance. These are in parallel, so you add the reciprocal of the resistances, but then that gives you the reciprocal of the effective resistance, which you have to then reciprocate one more time. Okay? Good deal. And calculators are so nice to do that for you. Okay. How about example 2 at the top of 479? Let's see if they have that drawn for us. I think they do. This time, circuit B is equivalent, well, okay, we'll do the work here. Okay? What we have here? We have a R1 here in series with the combination of R2 and R3. So what are we going to have to do? Determine an effective resistance for these two so we can add to that. What would be the effective resistance between those two? What kind are they? Say again? Parallel. So how do we find its effective resistance?
We add R2 and add R3.
Reciprocals. 1 over R2 plus 1 over R3 is equal to 1 over R4. Okay? And then that's in series here, so how do we combine those? You just add those because those are in series. So parallels, you add reciprocals. Series, you just add. Okay? So the first thing you do here is 1 over R2 plus 1 over R3 is equal to 1 over R4. This one. So once you get 1 over R4, you reciprocate again, and you get R4, and then you do R1 plus R4 is equal to R5. There's your equivalent resistance of the whole circuit. Add resistors in parallel, add resistors in series, add reciprocals of resistors in parallel. Okay. Got it? Okay. Let's see if they have a picture for example 3. No, they don't. Shame on them. Okay. You know what I forgot to do this time? Okay, I forgot. Did I? Yeah. Forgot to open my white page. Okay. All right. Now it's open. Example 3. Find the total current in the circuit shown in 1753. Here's 1753. We have a, whoa, let me get my pen back. Okay. We have a voltage source here. E is equal to 115 volts. More than likely not a battery, but alternating current. Okay, you come up here and you have a parallel situation. Okay, on the top leg of the parallel you have a series situation where you have R1 of 10.0 ohms. Then it connects in series to R2, which happens to be 32.0 ohms. Okay? And on the lower leg of that parallel system, we just have R3, which is 19.0 ohms. Okay? And that comes back around to the downside of the battery. Okay? That's what we've got. And what they're asking for is the total current, I, in that circuit. Okay? What would be your suggestion for how to get there? And there's at least 2 different ways to do this. You might think of more than 2. What would be your approach?
I'm just all for
So,
I is equal to E over R.
okay. Which R are you talking about? Oh, their effective resistance. Okay. The trouble is you don't know. Okay. 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 If what you said was R effective, so the total R is equal to V over I, is that what you said? Or you said it the other way? You said I, okay. Okay, got it. That's why I couldn't hear well, so, okay. So I is equal to V over R. And that's the effective resistance. So, we're looking for I. We know V, or I'm going to go back and make it E just so it won't be as confusing. Is that okay? Okay. But we don't know R. So we've got to come up with effective resistance. How do we get that? The effective resistance over that. Where do you start? Second?
Is it the sum of the resistance?
Okay. You can add these 2 together because they are in series. So if you want to call that R3, you could. No, R4, you could. And that would be 10 plus 32 is 42.0 ohms. That's the easy one. Yes, ma'am. Okay. Thank you. Okay. Everybody agree? That's a good first step. Now, do I need to draw what we have then, or can you picture it mentally in your head? Okay, that now, R4 is in parallel with R3. Now you add the reciprocal resistances. So 1 over R, this R you're looking for down here, is equal to 1 over R3 plus 1 over R4. It doesn't matter which order you do them. So that would be 1, yuck, drives me nuts. What's that? Yeah. So that's 1 over 19 plus 1 over 42. Okay. Now, here's a little clue here. Since down here in this formula here, that's a 1 over R, isn't it? It's an E over R. So when you find your 1 over R here, don't reciprocate unless they ask for that R. If they don't ask for it, all they ask for the I, just take that 1 over R and multiply it by E, and you'll have the answer. Okay? It's the same thing we did before. This is the same as E times 1 over R. Like E over 1 times 1 over R. Multiply the numerators, multiply the denominators, right? And once you get this 1 over R, why mess with reciprocating it? Then to go back and divide it, just multiply it by E, and that'll give you the same answer. Or if you want to, you can reciprocate it and then divide it. It works the same way. It works the same way. So what do you get? Effective, or 1 over effective resistance is, however you want to do it. You tell me. Either tell me what 1 over R is or what R is. I don't care.
Okay, so what I did was, I did it like the 19 times the reciprocal of 19 added to the reciprocal of 42.
Right.
I got 13.08. Well, I did it the first way you showed me.
Okay.
So I got 13.08.
That's once you reciprocate one more time. Right. Okay. So the R then is 13 point what? 13.0819. Okay. Now, and then you take the E, 115, 115, divided by 13.0819. Okay.
I had a bigger answer than the book got.
What's that?
When I took the 115 and divided by the 13.0819, I got 8.79, but the book got 8.78.
Okay. You got 8.79, and that would be amps, and they got 8.78 amps. Okay? I'll tell you why. They rounded this to 13.1. Okay? That would be ohms, either case. And what I suggest, unless they ask for the effective resistance, which this problem didn't, they just said find the total current. I would leave as many digits as your calculator does, then do the division, then only round your final answer. Because what they did was introduce, and here's what you call it, round-off error. Okay? And you see, by rounding here, you make some uncertainty in that last digit, the third digit. So when you come down here, you have uncertainty in that digit too. So both of those would have been acceptable answers. I don't take off if you're off by 1 or probably even 2 in the last decimal place. Okay? Because that can happen because of round-off error. I don't know whether it's you making it or them making it. I just give you credit for it. Because in reality, you're not going to measure ohms, amps in 8.78 or 8.79. If you get 8.8, you're lucky, okay? Because most amp meters are not going to be that good, okay? This is just sort of a make-believe problem here. All right. Now, that was example 3. Yeah, 13. Wait a minute. That wasn't example 3. Oh, wait. Oh, the answer's on the next page. 8.78. Got it. Or 8.79, I think, is more precise. All right. Enough of that one. Ready for example 4? Yay or nay? Okay. Example 4. All right. Find the equivalent resistance in the circuit shown in figure 17.54. Oh, isn't that a pretty one? All right, let me draw it out here. Here's your potential difference. E is equal to 120 volts. That is almost certainly AC. Even though they draw it like a battery, that's AC. Okay? Now, we come up here and branch into a parallel sub-circuit, okay, where you have R1 up here being 7.00 ohms, okay, R2 here being 35.0 ohms, okay, and finally an R3 down here that is 25.0 ohms. All right. Okay. They all connect there. And then you go down to the south side and you have a 2 unit parallel arrangement where your R4 is 20.0 ohms and your R5 is 62.0 ohms. And that finally goes back up to your lower side of the battery. All right. Now, it says find the equivalent resistance in that circuit, shown in that figure right there. Okay? What would be your approach? What would be your approach? Second? Okay. On the top ones, we're going to do a reciprocal relationship here. So you tell me what to write. 1 over R1 plus 1 over R2 plus 1 over R3 is going to be equal to, let's call it R6, okay? Okay.
So that's going to be R6.
Why not? I mean, you can name it anything you want to. Just don't use R1, R2, R3, R4, or R5 because those are already used. So I just use the next one. You could all call it RU for upper. I mean, you could name it anything you wanted to. Just not one of those names. Okay? Now, y'all want to plug away and tell me what R6 is? Say again? 67? Is that what you said? I don't think so, because it has to be less than the least of those. So it's less than 7. Did you say 6.7? Okay, you add the reciprocals, just like I showed there. That sounds reasonable because it's less than 7. So you get R6 is equal, say that again? 729, okay, ohms, okay? Now, what about the lower two? What are you going to do with those? Okay, so that would be 1 over R4 plus 1 over R5. And that's going to be 1 over, what do you want to call this one? R7. That's a clever thing to call it. Okay. You call it R lower, RL, whatever you want to call it. Okay. And see what those give you. R7 is, or yeah, R7 is 15 point what?
15.1219.
Okay, that'll be ohms. Okay. Now, you tell me something about R6 and R7. What would you say about them? You can, if you want to, redraw this to represent that. The same E here is equal to 120 volts. And it goes up, but now you put R6 up here, and that's what it's equal to. And then you come along down here, and you run into R7, which is really ugly, and that's down here. So what can you tell me about those two? They're in series because the same current goes through both of those. So how do you come up with an effective resistance? What do they call it? Equivalent resistance? I can't remember. Where is this? Oh, there it is. Find the equivalent resistance. So this will be R. What would that be if theirs in series?
R6 plus R7.
Absolutely. R6 plus R7, which would be 19.85. Okay? 19.85. What unit? Ohms. But that's too many digits, so we're going to round that to 19.9 ohms. Okay? Now, I wouldn't be at all surprised if they don't say something a little different. What do they say? 9.8. Okay? And that's because they rounded, where we kept more digits there, and they rounded early, and they introduced round-off error. But it's not much. That's 0.05 ohms. Who cares? I mean, 0.05 ohms difference. It's most of the time you only measure ohms to the nearest ohm, if that. Okay, so yeah, it really doesn't matter. Those are perfectly fine. They got 19.83. We got 19.85. That's 0.02 of an ohm difference. Doesn't really matter. Okay. Now, while we've got this up there, it says what's the total current in that example. Now we're looking for I, the total current there. How are we going to get that? That's it, E over R. And we'll use our effective resistance that you just came up with. So that's going to be 120 volts divided by 19.9 or 8, whichever you want to use, ohms. And what does that give you? Very close to 10? No, very close to 6. Yeah, second? 6.06. What unit? Amps. Okay. I'm quite willing to live with that. Oh, look at that. They got the same answer. Good for them. Okay, so in the long run, that all worked out fine. So that was your example 5. All right. Ready for the summary? Let's get out of, I guess I'll hit escape. Okay, discard that and go back to that. Okay, and go back to current slide. All right, here we go. Here is your summaries again. Characteristics of both series and parallel parallel circuits. All right? In a series circuit, a pure series circuit, the same current flows through every element. So I, the total current, is I1 plus I is equal to I2, is equal to I3, is equal to I4. Same current goes through everything. So really, all you need is I. You don't need those other subscripts. However, the resistance is add. Pure add. The resistance of the first plus resistance of the second plus resistance of the third. The resistance is add. Now your voltage, this is the voltage supplied, the E, by your voltage source. And that's equal to the voltage drop across each resistor. So that's what your V1, V2, and V3 are. These are the voltage drops across those resistors with the same current flowing through each. All right? Now, in the parallel circuits, pure parallel circuits, now your total current is the sum of all your smaller currents. Every branch has its own current. Okay? Every branch has its own resistor, but they add by reciprocals in parallel. So 1 over R, that's the effective or equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on and so on. That's where you use your reciprocal key. And in a pure parallel circuit, the voltage across provided by the power supply is the same voltage across each resistance. If it's a pure parallel circuit, so all those V's are the same as your E. Because it's the same voltage across there. Okay. Make sense? All right. Homework exercises in this section, 17.9, do any of the odds 1 through 5. They use one figure. 7 through 11, they use another one. 13 through 19 uses another one. And 21 to 25 uses another. Okay? If you're interested in reading about electrical and electronics engineers, you certainly are welcome to. All right, we're not going to do 1710, even though it's sort of an interesting section. I imagine that somewhere in your work you will be using different instruments, but this doesn't go into enough detail, I think, that it would be beneficial to do it. Now, 1711 talks about voltage sources, and basically these are your batteries that were developed by, first discovered by the anatomist Luigi Galvani, whose name is mentioned there on page 487. It has a little blurb on that. Physiologist, he calls him, born in Italy. That sounds like an Italian name. His work inspired his friend Volta to continue, and Volta was more of a physicist. Okay? And then 1712 is talking about putting your power supplies either in series or parallel. I don't think this is going to be of any practical application to you, so we're probably not going to do that one either. If you're interested in it, it's worth a read. Okay? 1713 is electrical power, but I don't think that was one of the sections we said we were going to cover. Let me go back and check and make sure. Nope, it wasn't. Electrical power is pretty interesting stuff. It's just voltage times current, by the way, and it's real easy to mess with. Then there's other ways we can express that, but that's what it comes out to. And that, I think, finishes the chapter, what we're going to do anyway. There's a little thing on Tesla high-performance electric automobile. Pretty interesting there, too, worth a read. The glossary is worth a read. Formulas are worth reviewing. Review questions if you want to. Review problems if you want to. But remember, we didn't do all the sections, so I would only do those that we did. So I'm pretty sure I got them to run off your tests. I may have run them off myself. But let me see if I can find those. I wish the person who left, I'd have known she was planning to leave, I'd have given her a test ahead of time. Okay. What, we got 4 left? Shame, shame. Okay. Glad y'all are here. All right. Now, this test, 10 questions like the other tests, but like a few of them, this has several multiple parts. Okay? So, each piece of it won't count as heavily as the others have. Some of them have been 10 answers and they're 10 points each. If I give you partial credit when I can see something to give for. This has multiple parts. Okay? Let me find it again. And unfortunately, the way they do their test bank, they don't put your blanks in there for it. So number 1 has 1 answer. Okay? Number 2 has 2, so you can put 1 above the line and 1 below the line. List 1 is A and 1 is B. Okay? Number 3 has 1 answer. Number 4 has 1 answer. Number 5 has 1 answer. Number 6 has 1 answer. Number 7 has 1 answer. Number 8 has 3 answers. So you can put 1 above the line and 2 below the line. And just list them A, B, and C. Okay? Then number 9 has 1 answer. Number 10 has 3 answers. And wait a minute. Those are, oh, no, those are charges. Okay. I thought they were capacitances first. Okay. So you can put 1 above the line A and then B and C below the line. So be sure you give me 2 or 3 answers if those are called for. Okay. All right. Now, that ends that chapter 7. So let's go back to 17. Let's go to 18. Now we got 5 minutes. Let's at least get started in 18. And 18 is dealing with magnetism. Now just a little bit of review quickly. 18 is magnetism, and we're only going to do 3 sections there. And then 19 is alternating current electricity, which we really, believe it or not, we've been doing the fundamentals of it. We'll do a little more specifics here if we have time, because we got 3 sections here. We've only got 4 days left, actually 3 and 5 minutes, so we may not get too much into chapter 19. So your last test will be the final exam. I will give it to you next Thursday, not this coming Thursday, the following Thursday. And at that point, I'll let you know, because I have to make it up before that class, and I don't know how far we're going to get in the class, so I'll let you know which questions you'll do and which ones you don't. Now, one other thing I thought of before, let me make sure on this, because this test bank is so pathetic. Let me make sure that there are no surprises here. Okay, I don't think there are. Okay. I think they gave you everything they needed. Unlike sometimes when they left off a frequency or something like this. Yeah, we're going to work 3 sections in. Yeah, we're done with 17. Now we're moving to 18. And that test is on 17. All right. All right. Let's get our slideshow set up. We have 2 minutes. Okay. Let's see if we can at least introduce magnetism. Chapter 18 does deal with magnetism. Okay. Let me make sure we do. Yeah, I'm pretty sure we do. 18.1 and 18.2, and then we jump to 18.7. Okay, so remind me of that. Now, there's a lot of stuff here that is not the first slide we don't get to till another page. Let's hit a little bit of nomenclature and that kind of stuff first. So let's go back to this and go from current slide. Not going to have time to do much. Okay. Now, electricity really for a long time was nothing but a parlor game. You could shock your friends and that kind of stuff, but that's about all they knew to do with it. Until Galvani came along, found out it made a frog leg move, told his friend Volta. Volta pursued and started getting batteries, making batteries, creating batteries, and then you got some useful form of electricity. Magnetism, on the other hand, has been known about for the longest time. I don't know how long it's been that sailors have used magnetic compasses to help them steer the ships, because that's the only direction you have when you're out in the middle of the ocean. You don't know where north, south, east, or west is. Your compass is going to be your guide. Okay? Now, a few things they learned about magnetism. Every magnet has two poles. It's not true of charges. You could have a single isolated positive charge out here and be happy. You could have a single isolated negative charge out here and it would be happy. You cannot have a magnet with just the north pole. You can't do it, okay, at all. If you have a north pole, somewhere there's going to be a south pole. They always come in pairs. So that's the first deal, okay? Now, they show a bar magnet here, and they show a paper clip hanging on the end. If you were to take that paper clip and put it on the middle, it would fall right off. Put it on the end, it hangs on. Put it on the other end, it hangs on. But in the middle, not going to happen. Okay, so all the magnetic force is concentrated at those poles. Okay? Now, are those poles the same? They act the same. They attract paper clips the same, but not unless you get another magnet handy. So if you have, say, a compass, and you have a magnet here, and you take one end of the magnet and put it toward the compass, one of two things is going to happen. Either the compass is going to go toward the magnet, or it's going to go away from the magnet. What does that mean? This pole and this pole are either different or the same. And what would they do if they were different? They attract each other. If they're the same, repel each other. So if this one is pushing away a north pole, that means this one's a north pole. If you flip it around then and put that other in, then it's going to attract the north pole because this is the south pole and that's the north. Or it will repel that south pole. Okay? So every magnet has two poles, and that every time they are different polarities. Okay? Not the same. Okay. Now, I'm just going to give you this I don't think is in the book. There are only 3 naturally occurring magnetic materials. They mention one here, iron. Okay? And then they mention several other alloys of iron, but they all have iron in them. So iron is definitely one magnetic material. The other 2 are nickel and cobalt. You don't run into those too much, especially cobalt, but nickel and iron, nickel, and cobalt are the only 3 naturally occurring magnetic materials. And then you can have alloys made out of either combinations of those or mix something else with them, and you can have other types of magnet. But naturally occurring iron ore that is magnetic is called lodestone, okay? And its mineral name is magnetite because it's magnetic. Magnetite is exactly the same chemical material as hematite, which is just iron ore. The difference is iron ore, hematite, is not magnetic where magnetite is. And that's rather bizarre, but it's true. Okay? Most magnetic materials are non-magnetic. Wood, aluminum, copper, zinc, everything except iron, nickel, and cobalt. Okay? I think we're going to have to stop there and pick up next time on forces between magnets. We sort of talked about it a little bit. We will wind that up next time. All right, folks, don't forget to vote. Okay, please vote. I'm sick and tired of 13% of our population determining our candidates, and that's what happens in a lot of these elections where you only have 20%, 25% show up. Okay? That's just not right. Okay? All right, good deal. I'm going to end it now.